about about 15 years ago or so, I came over to the US for my grad school. And since then, I've almost always lived in big cities. I lived in New York, I lived in Boston, Pittsburgh. Again, hard to see the night sky. So then when we moved to Madison about 6 years or so ago, I was really glad to again being able to look up at the night sky and start seeing those constellations again. So brought back fond memories. Then I think the other day, maybe actually last year almost, a colleague of mine told me about the observatory and how you could go up there and there is public viewing there. So what I did was actually, sorry, just a moment.
I'm recording.
Okay, all right. Can you go outside, please? Yeah. So sorry about that again. Uh, so then what I did was sometime, I think about a year and a half ago, I took my son Ishan, who you have already seen. I took him along with me to the observatory one night. They were pointed at Jupiter that day. So we were able to see a tiny little red speck. Uh, Ishan was kind of disappointed because I had told him that Jupiter is the biggest planet in the solar system, so he was expecting to see something much bigger. But hopefully one of these days. Uh, I have another colleague who's told me that he is able to see northern lights, at least in some form, from here. And now that I'm connected to the Madison Astronomical Society, I'm hoping to take astronomy a bit more seriously at some point. So thanks once again. Uh, so uh, a little bit about my professional background. I'm a computer scientist by training. All my degrees are in computer science, but I also pretend to be a physicist or an optics person. I'm a director of this lab in the computer science department here at the university. We call ourselves the Vision Lab. Vision stands for Wisconsin Computational Imaging and Computer Vision. And the goal of my lab is to design new kinds of cameras for various applications, maybe in robotics, in industrial vision, and maybe at some point consumer photography as well. So yeah, so we design new kinds of cameras, and then again, one of these days, I was having a conversation with my son, with our son Ishan, and I was asking him a rhetorical question that Ishan, what should we do next? What should we do next? And he started giving me ideas about what kinds of new cameras to design. So he told me that maybe we should design cameras which can see through things, and then I told him that those kinds of cameras are already there. Imagine X-rays whenever you go through airport security. And then he just offhandedly said, Ishan, again, why don't you design cameras which can see in dark? And it was I started thinking about that, and it turned out that, of course, that's something which people have been thinking about for the longest time. There are many applications where you do want to do imaging in very low light, right? Think about surveillance, think about medical imaging applications, astronomy, of course, all of you know much better than I do. These days, another poster child of computer vision, AI, machine learning, is self-driving autonomous cars. Again, you would want these cars to drive not just in good lighting conditions, but also during the night, right? Um, and again, these are just few snapshots, uh, but imaging in low light is just for me one of the almost the holy grails of imaging and photography. And I like to show this one example. It's kind of an extreme example, but you know, some of you may have seen this. But at first glance, at least it looked to me, as if there was a hole cut out in the photograph in the right? I thought this was one of those pictures where you cut out a hole and then you want to fill it in using some computer science techniques. But this is actually the picture as taken by a camera without any modifications. And I'll just play this video here. So what happened here is that there is this another mannequin head here, which is coated with this special material called Wanta black. which absorbs almost all the light falling onto it, which means that we don't get any light from this object, which makes it very hard to tell what it is or what its shape is. So here is a video.
One of the bronze masks that were previously coated with Vantablack S-Vis, and the same ones that were on display in the London Science Museum. So we removed that coating and replaced it with this new coating, and thought this would be the best way to demonstrate the level of performance under normal lighting. So you can see here we shot this with a Sony RX100 IV in high resolution, and hopefully the detail.
So yeah, I mean, this is an extreme example, but it kind of shows in a way the importance of being able to image in low light. The idea being that if you don't get any light back from the scene, then it's just very hard to tell what you're looking at, of course, right? It makes sense. Again, here it looks like a hole, but there is actually a real 3D object here, right? By the way, this is a small enough audience, so feel free to interrupt me at any point. I'll try to monitor the chat, but again, it's a small enough audience. Feel free to unmute yourself and ask the question. Yeah. So
detail or the
now, one way to take a picture in extremely low light conditions is to use these very specialized low light cameras. These are these EMC CD cameras. Now, these are usually expensive. They are quite bulky, and sometimes they need super cooling as well. So not really suitable for consumer devices, right? Now, fortunately, there is a new emerging sensor technology called single-photon avalanche diodes. It's a mouthful, so we are going to use SPADs for short, single-photon avalanche diodes. Now, the interesting thing with SPAD is that they can detect individual photons while maintaining a high signal-to-noise ratio and low cost as well. So we can usually, we can think of a conventional camera's pixel as a bucket, right, which collects photons. And usually a photon is, of course, the minimal light particle. Now, usually a conventional camera pixel would need to collect hundreds to thousands of photons per pixel to create a good, reasonable quality image. But a SPAD pixel here on the right, it is a much smaller bucket. You can almost think of this as a teaspoon that holds only one photon at a time. But it can detect the arrival of that one photon very precisely, which makes it extremely sensitive in low light, right? So there is the low light sensitivity, but SPADs can also work at room temperatures now. And finally, very important, these are compatible with the current CMOS sensor fabrication pipelines. So again, for those of you who don't know, CMOS is really the camera technology that's in almost all consumer cameras, right? So it's now can be done very cheaply at scale, which means that now these SPADs, these can also be manufactured at scale at low cost and fairly compact size. In fact, some of you may have heard of the new Apple iPhone. It has a LiDAR chip in there. It has a 3D depth camera. So that LiDAR chip is already based on these SPAD pixels, that's these SPAD sensors, which means that this technology is already in consumer devices. So you can imagine how expensive can it really be in the long run. I mean, right now, what we have is still very low resolution. I think about 20 cross 20, or I think something like that, maybe 50 cross 50 pixels. But this continues to evolve. So, because of all these nice capabilities, these SPAD sensors are driving many, many new interesting applications. People are now using these to look around corners. We call this non-line of sight imaging. These are used quite a lot in microscopy, fluorescence microscopy, even LiDAR in robotics applications. So almost any application where inherently you are photon-starved, you don't have enough light, SPADs are starting to play a major role. So this was really the status about 3 to 4 years ago, when these SPAD devices were still very expensive. We had one in our lab. This was just a 1 pixel device, and it was about $10,000. Because these were still considered mostly scientific devices designed for niche applications. And the other thing was that for most of these applications, the SPAD had to be coupled with a laser, which send in some light pulses into the scene. So we call these active applications because the SPAD is coupled with an active light source. But the next question that we started thinking about was, can we use these SPADs not only as these specialized scientific devices, but as more general purpose mainstream cameras? And for them to be used as a mainstream camera, you have to use them as a completely passive device, just like your normal cell phone camera, which can take pictures passively without the help of any extra laser or anything, right? And the reason why this would be interesting is that, if there are going to be any benefits to SPAD-based passive imaging, then this could really open up SPADs to a very broad class of applications, from photography, robotics, computer vision, hopefully even astronomy at some point. Because if you really think about it, most cameras and sensors in the world, they do not have a laser with them, right? So they're passive. So this could be quite interesting. So then, yeah, this is when we really started thinking about, although right now these are mostly scientific devices, but can we, in the long run, can they really be used as a more general purpose camera? Now, one of the biggest hurdles at that point, at least, was that we only had, very low resolution cameras. Like actually, we only had 1 pixel, and then people were at that point starting to think about maybe a 32 cross 32 pixel device. Again, not very high resolution. But then something remarkable happened in the last 2 or 3 years. There's almost a single photon camera revolution that suddenly people got interested. Some major companies got interested, like Apple, Sony, Samsung. They got interested in this technology. And now, just this last year, we were able to come up with world's first 1 megapixel SPAD camera. Now, 1 megapixel doesn't sound that much now. Most of our cell phones are already more than 10 megapixels. But given that this is still a very new technology with this single photon sensitivity, 1 megapixel was a big landmark here. And this continues to evolve. Now, I've been told that there is no fundamental hurdle in going to 4 megapixels or even down the road 16 megapixels. So that's when we are really getting into the territory of a consumer grade camera with single photon sensitivity, right? So I just feel that because of all these factors, because of these interesting capabilities, this is really the right time to start exploring the potential of these sensors, not just for scientific applications, but think more broadly for consumer photography, computer vision, robotics, and at some point again, astronomy too. All right, so this was just a quick background on these new kinds of cameras. So any questions at this point? Anything? No? All right, cool. So I want to talk a little bit about how a single photon camera captures a photograph, right? So let's say we have a single photon camera, and it's a bunch of pixels. And you can think of your camera as an array of pixels, right? Each one here is a pixel. And again, we said that you can think of a pixel as a photon bucket. It collects light, right? So let's see how this light collection happens. And we'll start with just a regular camera, conventional camera. Think about your cell phone camera. Here is your photon bucket, and there are photons coming in, right? Each ball here is a photon. Now, the important thing here is that the arrival of photons, it's a random process, meaning photons arrive randomly over time, right? Which means that if we expect this bucket to, let's say, collect 3 photons in a certain duration of time, then if we repeat the measurement multiple times, we may actually measure 3 photons. Or another time, looking at the same scene point, this bucket may collect 6 photons, or it may collect 0 photons too. So there is this inherent randomness, uncertainty, that just happens because of the quantum nature of light, right? We can never be fully certain what we're going to get, right? We can say on an average, we are going to see 3 photons, but in any particular measurement, there is some randomness, right? But now, this is for a regular camera. Again, we go back to our single photon camera, which, remember, again, it's just a teaspoon, not a bucket, meaning it can only hold one photon at a time, which means that anytime this thing sees one or more photons, it will just return a value of 1, right? And it will return a value of 0 otherwise, right? So this is an important point. What this means is that now if I look at this image taken by your single photon camera, each pixel will only have two possible values, either 0 or 1. 0 means it saw no photon, and 1 means it saw one or more photons. So maybe you can try to visualize what that image would look like. Like whenever we look at like a normal image, there is a full range of intensity values, right? Some pixels are brighter, some pixels are darker. Usually there is a continuous range of values. Right? So dark means 0, and 1 usually means 100 or 1000. But these single photon cameras are going to capture these very special kinds of what we call binary images, meaning each pixel is either 0 or 1. Right? So let's maybe look at some example images. So here's an example image taken by a single photon camera. Right? So we call this a quanta image, because it's heavily quantized. Right? There's only two values, two levels, 0 or 1. Right? Now you can see that this image also looks very noisy. Right? Doesn't look like a clean image. But the key thing here is that because SPADs, these sensors, they directly record arrival of individual photons, right? Which is a discrete event. So there is no analog to digital conversion that happens, which happens in regular cameras. So the way regular cameras work is the light comes in, then which generates an analog current, which is then converted to a digital value. And that conversion process leads to some noise in the images. But here, in these single photon cameras, there is no analog to digital conversion. A photon arrives, which is a discrete event. It's directly recorded as a discrete event, right? So which means that any noise that you see is just due to randomness of photon arrival, which is really just the inherent property of light. Right? So in other words, the camera itself is not adding any noise of its own. Right? So this is really just a fundamental limit, this noise of light. Any camera, even human eye, there is this noise that we call short noise due to randomness of photon arrival. This happens in any camera, right? All right, so yeah, so this one image, of course, it doesn't look that interesting. It's very noisy. There's only two intensity values. But what we do know is that if we capture multiple images of the same scene over time, then because of this randomness, we are going to get different image every time, right? Because each pixel will record a 0 with certain probability and 1 with certain probability, right? So here is one example sequence of images taken of the same scene. Now we get this series of 2D, a series of these binary images. Now, of course, there is randomness here, but one thing that we know is that statistically, a pixel that is dark, like here, it will see 0 more frequently, right? It will be 0 more frequently because it just doesn't get that many photons. Whereas a bright pixel here, it will see 1 more frequently because it will get more photons more frequently, right? So that's really the key observation here, that each individual image may be very noisy, but if you look at a series of images over time, then just by looking at the statistics, you can start maybe deriving some inference about how bright a pixel is, right? Meaning, again, this pixel, if it sees 0 more times, then maybe it's dark. This pixel sees 1 more times, then it's probably brighter, right? So again, higher the count, higher the number of ones that a pixel sees, brighter the pixel intensity. So there is a more formal mathematical expression, which I'll skip. This is an informal talk. But intuitively, this is what the process looks like, right? Now, the other interesting thing is that these cameras, they can capture these 1 bit, or these binary images at very, very high speeds. So just to put that in perspective, when we think about the cell phone cameras, the regular cameras, they capture videos at maybe 30 frames per second or 60 frames per second. But these cameras can go up to 100,000 frames per second right now. So it's at 3 orders of magnitude, so 1,000 times faster. Which means that now I'm getting these binary images at very, very high speeds, right? So here is again one image, right? Now let's say because I can capture these at high speeds, let's say I capture 10 of these in very quick succession and add them together. So can you try to visualize what that added image would look like? So just take a few seconds to try and visualize. Now let's say I have 10 of these images, and now I add all of them together. So now the interesting thing is that each pixel in this added image, each pixel will have a range of values, not just 0 and 1. Each pixel will now have a range of values between 0 and 10, so more continuous gradation. So it looks something like this. Right? This is a sum of 10 images now. So you can see that now the structure is kind of emerging better, right? So we can continue. We can get an even better image by adding 100 images. And now you can even start making out some details here in the background, right? So we can keep going. Here's some with maybe 1,000 images. And now the noise has gone down quite a bit too, right? So yeah, and again, we can keep going, right? And until the final image quality will only be limited again by just this photon short noise, which, as I said, in some sense is a fundamental limit. We cannot do much better than that, right? So then a natural question to ask here is, why don't we just keep going, right? If we know that we can continue to improve the image quality by adding more and more images, so what stops us from taking not 1,000, but maybe 1,000,000 images and then add them together to get a very, very high quality image? So any ideas?
Motion?
Absolutely, right? If everything was perfectly static, right? If nothing were moving, neither the scene or the camera, then yes, we can do that, right? If we have all the time in the world, we will just add, millions of images, and we'll continue to get better image quality. But uh, in most interesting real-world scenarios, there is motion, and here's what happens, right? Whenever there is motion, a single camera pixel is not looking at the same scene point during the entire sequence, right? Which means that photons from a scene point, they get distributed over multiple pixels, right? And this creates this motion blur here. Which means that, there is obviously this trade-off between noise and blur, right? We can either take a short sequence on the left, which will not have blur, but it will be very noisy. On the other hand, we can take a longer sequence, less noisy, but more blurred. Now, this trade-off is not specific to this particular imaging modality. This is one of the most fundamental trade-offs in any kind of imaging, including conventional cameras, right? I mean, we have all tried to take images in the dark. It doesn't work because either it's too noisy or things just start getting blurred out. So the question then we asked was, is there a way to overcome this trade-off? And overcome may be too strong a word, but maybe mitigate this trade-off at least. So that's what we really started set out to do. And the basic idea here was that, or the problem here first is that we have this series of images that we capture over time, right? We call this quanta image sequence. Now, if we just naively add them together, then we get a blurred image, something like this. But now, instead, if you could somehow measure the amount of motion between these individual frames, and then if you could compensate for that motion, if you could warp these individual images to compensate for the motion before we put them together, then maybe there is hope that we can recover a high quality image with both low noise and low amount of blur. So this intuition was the idea behind this method we developed called QuantaBurst Photography. And the idea was that we're going to use this single photon camera, which is going to give us these binary noisy images, but at very high speed, so about 100,000 frames a second. Meaning, again, even in a very short exposure time, even if we have like 100 milliseconds, we can capture about 10,000 of these frames, right? That's really fast. So now what we're going to do is take this sequence, and then we're going to compute motion between them. Then you're going to align them. And then after the alignment, hopefully, we have compensated for the motion. And then again, if everything works the way we expect, we can then finally merge them into a single high quality image with low noise, low blur, and even a high dynamic range. I will get to the high dynamic range part later in the talk, right? So just to put this in context, again, this idea of burst photography, it is now quite popular in consumer cameras too, and some of you may be using it now. What happens is, I think this was in Google's new cell phones, meaning if there is this burst mode there where you click, instead of capturing one photograph, it takes a short series of sequence of photographs, about 5, 10, 15 images, and then it kind of compensates for the motion between them and then puts them together. So the overall goal is still the same, to take high quality images in low light, right? So again, there's a team at Google which has been doing pretty phenomenal work in that space. So again, in conventional cameras, in conventional burst photography, we take about 5 to 10 images or so. Now, the main difference in QuantaBurst photography is that we capture not 5 or 10, but 5 or 10,000 images, which then allows us to do this motion compensation at a very fine grained level, almost at the granularity of individual photons, which means that now we can start dealing with very high speed motion in extremely low light conditions, right? So that's again the very high level, almost a bird's eye overview about on how this method works. So any questions about, again, I'm skipping, I've deliberately skipped many details, but I'll be happy to any questions at this point.
So Moa, you said earlier that some of this technology was already appearing in consumer cameras, and this is a good example because I know that Apple and Google are using this burst mode thing.
Mm-hmm.
Is that actually using the single photon avalanche technology that you're talking about? So they're not.
Yeah. No, not yet. No, they are doing it on regular cameras. So that's why they have to be limited to only 5 or 10 images. But now we are saying that now you can almost think of QuantaBurst photography as burst photography on steroids, right? I mean, you can do this at very, very high speeds. Now, the technical challenge there is, because now here each individual image is extremely noisy, how do you really compute motion reliably? So that was really the technical innovation here, that we demonstrated that it is actually possible to compute motion and compensate for it, even for these heavily noisy images.
So you don't have to answer this question if you can't, but I know you have a variety of different funding sources. Are people like Apple and Google, are those big companies that obviously have a great investment in camera technology, are they interested in your work?
We haven't been contacted by Apple or Google directly, but I know that it is on their radar. We have been talking to other imaging companies like Sony, for example. Sony is a world leader in camera technology. So we have been talking with them, and they have shown quite a bit of interest in this.
Yay, Sony.
But this work was funded by the government. This was an NSF, National Science Foundation, and an Office of Naval Research project.
I do have a question. Is this computationally intensive, or are you doing this in some other way, stacking the images and doing the work you're talking about?
That's a great question. This is extremely computationally intensive right now. So
is that kind of the limitation right now, the computational intensity?
It is one of the two main limitations in my opinion. One is, of course, the computational intensive part. And the second is that these sensors, these are still very power hungry, because they consume some amount of power for every photon detection. So these are the two major practical hurdles, at least in my opinion.
Can I ask what range of energies, what range of energy photons can these detect, or does it depend on how you design it?
That's a great question. So I think right now this technology is fairly mature for visible range and maybe near infrared too. So I would say between 400 to 800, 900 nanometers wavelength. Uh, I think there are some research groups which are trying to take this to far infrared, but then you have to start looking at different kinds of materials, not silicon, and it starts becoming more challenging. Then you have to look at materials like InGas, indium gallium arsenide. That's a little more challenging. Yeah. So yeah, just to give you an idea about the computational complexity here, right now to create one image, it takes us about half an hour because we are putting together these 10,000 frames, 10,000 even in some cases 100,000 frames together. It takes us about half an hour on a big computer, not a cell phone. With some optimizations, we were able to get it down to 5 minutes, but still that's nowhere near practical, right? And that's an active research area now, how to make it more practical. Yeah. So yeah, I want to show you some results now. But of course, another practical limitation is that right now this is what our camera looks like. Of course, this is the chip here, but right now it needs these two big power supplies. But now, hopefully, this can be miniaturized on chip soon. Right now, this is still relatively low resolution because this is still a research grade technology right now, at least. So the camera that we have is about 512 by 256 pixels, and not very high resolution. So please don't expect very high quality images right now, just to set the expectations right. But,
could I ask, are you building the chips yourself, or are they commercially available? Are you working with engineering to build them, or how are you getting the chips?
That's a great question. So these things are not available, at least at this resolution. These are not available off the shelf. You cannot purchase them. So we are collaborating with a research group. They are based in Switzerland, and they are the leaders in this sensor technology. So that's why this is a research grade device. But from what I've been told that that research group has a spin-off company too. So they are an academic research group, but they recently started a company which is now starting to commercialize and sell these chips. Yeah. Yeah. Okay, so here is one example sequence that we captured in the lab. Now this is a real sequence now. So far what I was showing was more computer simulation, but this is a real sequence. And in this sequence, I mean, this was a fairly well lit scene. So here on an average, each pixel gets about 1.2 photons per frame. This would correspond to, I don't know, maybe like a room lighting about 500 to 1000 lux or so. This was about 2000 frames. And then in this case, there was a scene that we set up and we're moving the camera itself, a fairly large amount of motion, which means that if we naively just add things together, then we get an image like this. So a lot of very strong blur. It's hard to tell what kinds of objects there are in the scene. But then now we used our approach where we compensated for the motion and we could get something like this. Right, now you could see that there were these three toys on the table. There are a few artifacts here, which are more of a sensor artifacts. There were a few dead pixels on the sensor. So, yeah. So yeah, so here's now another example, similar scene, but now this is much, much darker. And you can see, now the white dots here, they denote the photon detection. They're much sparser than the previous sequence. Again, this is because this is much darker. And here now, each pixel gets less than a tenth of a photon on an average per frame. So it's very dark. Just to put this in terms of lux, I would say this would be less than 10 lux, getting close to 1 lux maybe even. But with that, again, we captured long enough sequence, and then we did the motion compensation, and we were able to recover this image here. Right. Now, this is, of course, much more noisy than before, but given that over the entire sequence, we saw only about maybe 50 photons per pixel. That's actually quite, for me, it was quite remarkable.
So Mo, when you say that's a low light situation, how dark?
Yeah, so this was done indoors, and we did not have any strong artificial light. If I have to estimate the lux level, I think it will be about single-digit lux values, probably maybe 1 to 5 lux or something like that. So still not super low, but we are now working, trying to experiment with super low lux levels, like maybe 1,000th of a lux or something, night sky as well. So right today I don't have results with that, but we have done some lab experiments, and it seems to work reasonably well.
Is there any hope you'll be able to image the earlier video you had of the ultra black? Or is that simply too low a light level to be able to do anything with it?
You mean the one with the mannequin?
Correct.
I will have to estimate the number of photons actually. But I think given a long enough sequence, we should be able to image that. But that's a great question. We should try that out. Yeah.
When you're doing the image additions, are you using right now a general purpose computer to do it? Is this the type of thing that ultimately would end up being built into silicon, like the GPUs that Nvidia and so forth make? Or
that's a great question. Yeah. I think we are doing a combination of general purpose CPUs as well as GPUs right now. But right now, the amount of computation is just too large for even a GPU to handle. So I think eventually what we'll have to do is kind of offload all this computation on chip itself as close as possible to the sensor. Because that's the only way to deal with this level of computation. Yeah. So here's another example of a scene. Again, this is a sequence of these binary images. And then on the left here is what you get if you just simply add things together, you get a lot of blur. But on the right, you see this sharper image. Now, another kind of interesting side effect here is that now, because the amount of motion between two successive frames is very small, it's almost like sub-pixel motion, you can get some kind of a super resolution. Meaning the final image, the total resolution can actually be more than the individual images. And again, the high-level intuition is that because now the motion between successive images is less than 1 pixel, you can kind of create this super resolved grid of pixels and populate it using samples from successive images. And then you can combine these images at the super resolved grid. Right? So I just want to show you an example with this. On the left is if you do this merging without super resolution, and on the right with super resolution. So you can see more details now on the right. Especially if you look at the close-ups, you see more detail here. Right. So this is still very research grade. I mean, again, we still haven't really stress tested it, pushed it far, and we are, as we speak almost, we are now starting to take this outside the lab. The other day we saw some sequences in my garage in the night, just to see whether it can do things in complete dark. So here are some more examples where we took this outside the lab now. So we are switching between blurred images and the motion corrected images. So here's another interesting example. We are not really making any strong assumptions on the kind of motion. We're not assuming that things are only moving rigidly. Things could be moving non-rigidly as well. So this method can handle high speed and highly complex motion. So here's an example of Sergio. He's my graduate student, PhD student, who, by the way, actually did all the work here. I'm only presenting it. So here's an example of Sergio. He's playing the guitar. And again, these are two ways to do this averaging. On the left is like a long sequence. You see a lot of blur here. And on the right, you see a short sequence, so you see a lot of noise. But now with the right motion compensation, you can get an image where there is small amount of blur and low noise too, right? With the right proper alignment, right? And then from here, it's not that hard to imagine that you can extend this to recover a video, not just an image, right? So one way to do this will be simply to shift your averaging window in time, and you run this method multiple times over time, right? So you can now recover this high-speed video as well. Again, as I said, right now, these images are still relatively low resolution. As you may have noticed, these are not color images because the camera that we have is only monochrome, doesn't have color, but still kind of an interesting technology.
Mohit, when you talk about the computational intensiveness of this photography, I think we can infer, some of the scale of what you're talking about by the fact that you are in fact a computer scientist and your department is computer science. What kind of hardware are you talking about? Off-the-shelf processors, or are you using a specialized, array of chips? How are you doing the computational part of this?
Yeah, as I said, right now we are still using mostly off-the-shelf stuff. It's just off-the-shelf CPUs and some GPUs, some of these Nvidia GPUs as well. But even those are not nearly enough to do this kind of computation in real time. So eventually, I think there's almost a separate research project here to come up with new hardwares that can deal with this amount of data in real time. It will take some time.
I'm just kind of curious because when you take a look at what the Large Hadron Collider and things like that are using, the amount of data they're using, they must have some chips that are able to respond extremely quickly. I know they're doing a lot of early filtering to reduce the data, but they're producing ungodly amounts of data and processing it pretty quickly. Is there anything there that you can look at all, or is that kind of in left field for me?
The way, I to be honest, I'm not that much of an expert on the computing hardware, but from what I know, these big physics experiments, the way they deal with that kind of data is just by brute force. When we talk about their chips, it's really a room full of machines which crunches all the data. So that's how they get their speeds.
So you're looking for an elegant solution rather than brute force.
Something which can fit into a cell phone, right? Eventually.
Supercomputer on my cell phone.
Well, the computer that you have right now would have been considered a supercomputer 20 years ago, right?
So is there the idea to design a specialized chip that would do this one purpose essentially and do it very well, but wouldn't be useful for other things? Is that kind of the idea?
Yeah. It may sound like a niche thing to do, but if you look at most cell phones right now, they already have a special what we call IPU, which is image processing unit. So there is a dedicated processor which does only image processing. So what you would need is an IPU, which is kind of tailored to this kind of data.
Right. Okay.
Yeah. But yeah, we
You
already
had mentioned that you were using some off-the-shelf Nvidia GPUs, and I was just wondering, as a researcher, do you have a channel that gives you special access to those, or do you have to wait for months or pay scalpers like the rest of us?
you know, right now I don't have that kind of cloud. I'm still an assistant professor. Hopefully down the road, you know, maybe I can get some direct access. But right now I have to go like everybody else.
I just got an RTX 3080 after waiting on a waiting list for 5 months. So that's what prompted the question.
You know, same for me. We have been trying to buy a 3090 and it's been 6 months and we haven't been able to get one.
Wow.
Yeah. But I'm sure there are people in the university here who I'm sure have much more cloud. They can get something. So maybe I should make friends with them.
Does Amazon or any of the large computing environments, do they offer GPU as a service?
They do. You can, there is a pay-per-use service. So what you do is you upload your data and computation on their web servers, and then you pay per amount of time. So you can rent, yeah. In fact, right now, I think that arm of Amazon is one of the most profitable ones. This arm called Amazon Web Services.
I'm a little curious about the, like I'm in radiation oncology and we use deformable registrations to try to match different types of images to each other when the patient's moving or deforming. And so this is an interesting part of it for me. I mean, I imagine it must be quite different though, because especially with some of those low light single frames where you can't see much, that I don't know, does it work very differently? Is it a totally different kind of process?
I mean, at a conceptual level, I would imagine that it's probably not that different. But I think the devil here is in the detail. It's in the engineering. That you really have to think very carefully about how would you compute motion reliably when you don't have sufficient signal to do these kinds of comparisons across planes. So it really is a lot of algorithmic tricks here that we are using. But I would say it's probably at a fundamental level not that different.
What computer language are you programming in?
Right now we started off with the MATLAB. Don't know if you are familiar with that environment.
Yeah.
It's like a very quick prototyping thing, you know, it's quick to program, but very slow. So that's hence the 30 minutes. But since then we were able to transfer that code into C++, which is a faster language. So that brought it down to about 5 minutes or so. Well, again, it's still not practical, but
I like that language.
Out of curiosity, is DARPA showing interest in this type of technology?
DARPA is interested in, I mean, they are always interested in low light, right? Because they always want to do surveillance, etc., without notifying them in any way. Now, they are interested in low light, but they're not interested in creating good quality pictures, right? They are interested in what can you do with those pictures, right? Can I detect people? Can I detect an object maybe in the dark? Can I maybe use this technology on a vehicle so that it can navigate around in extremely low light? Can
Or
it
around corners, or anticipate what's around a corner too?
Or yeah, of course, around the. By the way, yeah. So DARPA had this program called Looking Around the Corner. So we were part of that. And part of this work was actually funded by that grant too. Yeah.
There was an article, this is some years back, about the going around the corners, which actually depended on optics and reflection from surfaces to
Yeah.
look around the corner.
Yeah.
How does your looking around the corner, is that the basis of your looking around the corner, or is it something different?
It's very similar. So the idea is that when you want to look around the corner, of course, you don't have direct line of sight to that object, but you do get indirect reflections. So now the challenge there is you don't get that much light back from indirect reflections. So that's where again these SPAD devices come in. And in fact, the reason why the reason why our community started looking at SPADs was originally for this around the corner problem. But then what the question that we asked was, that's one application that's for me at least, it was a relatively niche application. So my question was, does it have to be limited to that application, or can we really convert this exciting technology into something more general purpose, something more mainstream?
If you do, you haven't talked, and you specifically mentioned you weren't talking about color, but if you do go to color, will you have to use the Bayer matrix on the chips, or is there some other way you can deal with color?
That's a great question. And again, this is happening almost as we speak. We have been developing a color version of these cameras now. And there is this interesting question, right? That over the years, people have been using these Bayer filters for conventional camera, which is array of red, green, and blue filters. But now, if you start looking at cameras like these, would we still go with Bayer patterns, or is there another pattern that's probably more suitable? So that's an active research topic in our lab right now.
So it actually is an issue of some sort of a matrix, some sort of a filtering process using multiple pixels to give you one pixel.
That's right. It will still be, at that level, it will still be quite similar. Just the arrangement of filters in that matrix, that may be different.
That was something I was curious about as well, because in radiation oncology, and we get with like CT scanners, they're working on single photon counting. And I think it's probably a different technology. I'm not an expert on CT, but they're able to recover the energy of the photons. And so if you were able to recover the energy of the photons, you wouldn't need any filters or matrix or anything.
That's right.
And I don't know is that possible with this kind of technology?
That's a great question again. So there was actually a company a few years ago, which it was called Foveon. It tried to do something like that with consumer cameras. So what they were doing was they were trying to determine the depth to which a photon penetrates the silicon substrate. From that, they were trying to estimate the energy of that photon, which gives you the wavelength.
Yeah.
I think they built some interesting demos, but the problem was that although that could be successful for like a CT kind of scenario where you are not that constrained by device size and power consumption, etc. It was just not very successful for consumer devices.
Okay. Because that would be really nice as someone who does a lot of astro imaging, that if you didn't have to deal with filters or Bayer matrices or anything, you'd get, it'd really be pretty interesting for our field. I mean, that's sure a long ways away, but.
Yeah. So no, related to that, what we have been thinking about is, yes, filters are ideally you want to avoid them. But the question that we have been asking is, maybe we cannot completely avoid the filters, but is there almost a minimal set of filters that we can use that can still give you color,
Right.
but don't absorb that much light? Because of course filters absorb light.
It seems that astro imaging ends up in a different category though, because for most of what we do, it's not moving. There's no motion, other than the motion of your tripod and the camera, the jitter. And if you can actually use external filters and just combine a bunch of multiple monochrome through filtered photos,
yeah,
that would be, I mean, that's a different solution for astro imaging.
But you're losing a lot of your photons from those filters. If you could collect all of them and sort them out by their energy instead of by filtering some of them out, you'd get a lot more data.
Right. The thing is, that is the limitation of using filters. But
oh, right, yeah.
If you use a bare matrix, I mean, you're losing, you know, end up with a quarter of the resolution. So, the idea of using the depth of penetration into silicon, that's an interesting idea.
And it depends, you know, for astro imaging, sometimes you're interested in a very narrow bandwidth of a very narrow range of a wavelength of light, you know, and that might be, seems like that might be a bit of a challenge for a chip to kind of detect the energies. It would seem to be more of a broadband technology than a narrow. I'm just guessing, but.
Yeah, but actually monochrome, if you're working in a very, very narrow band and you're essentially treating it as one color, then this would work very well.
Yeah, for sure.
I would think that would also cut down on the computational challenges too.
Yeah.
Yeah.
I mean, when you were talking about this, I think every one of us was probably thinking the basic technology you're using here is what astro imagers do, and that's essentially stacking. So I think there was probably a warm, fuzzy feeling right at the beginning of your talk.
Yeah, between stacking our images, say it's, you know, imaging for like several hours and then stacking all the images. And then you're also dealing with motion removal by using a guide camera to correct our mount and remove motion that way. But then also say if you're doing planetary imaging, you're also, or high power imaging, you're also concerned about motion caused by the atmosphere. And
well, and this would allow lucky imaging for deep sky objects.
Yeah. And lucky imaging is one thing that I really, really want to try next. You know, being able to see through atmospheric turbulence and seeing whether we can apply similar techniques. So actually, if you have any suggestions on that, I mean, one challenge here has been how to get access to a device where we can capture relevant data.
Well, you have a bunch of interested astro imagers here. Maybe there would be something something you could use of ours that would help you, especially for the astronomy part.
I would love that.
You into amateur astronomy too.
Yeah, I don't know if there is a mailing list here where I could maybe post maybe some requests or requirements. But if there is one, I would love to maybe connect with somebody here and see if we can capture some cool astro photographs.
yeah, Promega has a pretty good observatory these days. They've been refurbishing the what used to be the Madison Astronomical Society's observatory in Fitchburg, and now they've got a fully operational dome with a high-end Paramount and a pretty nice pair of telescopes in there.
Mm-hmm.
More questions? Go ahead.
No, I was going to say, Lawrence, I was thinking that if he does have a request like that, maybe somebody would be interested in working with him at YRS, one night of work or something like that. Somebody who's got the equipment to do it. I don't know, but it's a possibility.
Yeah, if you could maybe work together with somebody, even for maybe, you know, a couple of nights just to capture some interesting sequences. We would love to try our algorithms. And as I said, right now we are in the process of actually creating a color version of these cameras too. And we are hoping to get one by sometime in the fall. And it will have higher resolution too. So I think it will be great to make some good looking pictures.
I have a feeling if anybody participated in that, they'd end up with their name on a publication.
Yes.
And you know, it wouldn't be that hard to use a filter wheel for something like this.
Yeah.
Just to get the color data for that, because you know it's if you have it connected to a telescope that's tracking, you've got plenty of time, so it's not, going to be that sensitive.
And I have the feeling for the work he's doing, he doesn't need a really powerful telescope. Almost anything would work. It's just getting the photons from the sky.
Yeah.
Does anybody else have any other questions? Well, thank you very much, Mohit. That was a very excellent presentation, as you can tell.
A lot. Thanks a lot, Sergio, for coming, and thanks for doing all this great work. And yeah, if any of you is interested in learning more about the technology, looking at more results, there's more information at this project webpage. So yeah, once again, thank you very much for the invitation. It was a pleasure. Thank you very much.
Thank you.